Okay, let's head over to the software compilation. Here, the high-level code in which we compile is Rust code. And during this compilation, we are able to automatically inject annotations, which can be used for the verification of the code. So we use the Viper framework, which translates these verification annotations into an SMT model. And it uses an SMT solver, namely C3, to then verify the model and thus verify the Rust code. And the idea is that this verification of the Rust code then translates to the executable Rust monitor. Of course, this is a story for a different conference, whether this actually works and how we can achieve this. For here, we just assume that it actually does work. Now note that this compilation here is not for RT Lula, but for standard Lula, so Lula 1.0, which is the original Lula. It looks pretty similar to RT Lula. There are a couple of differences. One of the differences is that the offsets we can have are not just synchronous for the current value and the last value, but they also allow future offsets. So in our running example here, we have an input named altitude and we have an output too high, which checks a condition for 3 consecutive readings of the altitude. Hereby the 3 consecutive values are the last one, the current one, and the next one. So one major difference between Lula and RT Lula is that we have future offsets in Lula, but we do not have any real-time and we have no asynchrony. So when we compute something, then all streams will be evaluated. This kind of simplifies things in a couple of places. The future offsets, however, need some additional work. So what we have to do is we have to consider when can we compute values. So if we get a new value for the altitude, then we cannot necessarily compute the respective value for too high, because it refers to the next value of altitude, which we don't have already. So we have to delay the computation of too high by 1 step until we get the next value of the altitude. And this delay is manifested in the shift. And to compute the shift of streams, we once again have to have a look at the dependency graph. And here this is the dependency graph for the specification. As expected, there are 3 edges from too high to altitude with the labels -1, 0, and +1. And for this specification, we want to define the shift. And the shift here is based on a dependency graph where we say the shift of a stream S. For this, we take all edges that are outgoing from S to some other stream, and we consider the weights of the edges here. So starting with the altitude, there is no outgoing edge, so we know it just defaults to the value of 0. So the shift of altitude is 0, and this is the case for all input streams. And the shift for too high here, for this we take all outgoing edges, there are 3 of them, and they only differ in the weight, which is -1, 0, or +1. And we take the weight plus the shift of the excess streams, which is 0 because it's the input. So the maximum of these values is 1, thus the shift of too high is also 1. And the same holds for trigger because the shift dependency is pretty much transitive. So since we have to delay too high, we also have to delay the computation of the trigger. In addition to the shift, we also want to compute the memory requirement based on the dependency graph. And the memory requirement mu of a stream S is defined by this formula, and it depends on the shift again. Now here we have to take a different route. If we want to compute the memory requirement of a stream S, we have to check which streams do access the stream S rather than the other way around. So let's start with the trigger. So let's say S is the trigger, and we check all of the edges all of the other streams that access the trigger, which is none. So it defaults to the value 0, which makes sense because we don't have to store the value of a trigger. We compute it, we check whether it's true. If it's true, we alert the system, but there's no need to persist the value. Then for the too high stream, we once again check all incoming edges, which is just the one from the trigger. And the shift of the trigger is 1. The shift of too high is also 1, and the weight is 0. So 1 minus 1 minus 0 is 0, which also makes sense because we compute a value for too high, and this value is just used to compute trigger, and it does not have to be persisted again. It's just used in this one evaluation cycle. Lastly, for the altitude, we have once again 3 edges to pick from, and they only differ in the weight. Since we want to maximize this, this formula here, we want to minimize W, so we pick -1 here. And the shift of S prime, which is too high, this is 1. The shift of altitude is 0, and 1 minus -1 is plus. So here the memory requirement is 2. And once again, this makes intuitive sense because we need to access 3 different values of the altitude for the computation of too high. And since so we only have to process 2 values because we get 1 new value, we compute something, we can evict one of the 3 values and keep the remaining 2. So the memory requirement is also just 2. Okay, taking care of the shift in the memory requirement is important. The last thing we have to take care of is the different accesses we have. So fallible and infallible accesses. Here we have the usual accesses as before. However, for the 3 accesses we have, 2 of them are fallible, namely when we access the last value or the next value of the stream. And these accesses work most of the time, but we know that in the beginning of the evaluation here and at the end of the evaluation, they fail. And they only fail at these places. In the middle of the evaluation and of the monitor, they will never fail. And that's interesting information. For the last axis here, this is infallible. So we know that we only compute too high when we get a new value of altitude, so this axis can never fail. So all of them will always succeed. And this is quite interesting information that we can use. If we do not use this information, then we would get a naive implementation like this. Here, when we access the past value of the altitude, we try to access the respective value in the memory, here with the get altitude function, and this value is maybe there. We don't know it. And to decide this dynamically, we have to use something like the unwrap OR function, which says if the value is here, we take it, otherwise we take 0. And these 2 unwrap OR functions are conditionals. And conditionals are always way slower than normal instructions. So we try to avoid them. Since we know, however, when these different accesses succeed or fail, we can use this information in the translation. And this information is, in quintessence, 3 different phases of the evaluation. The first phase is the prefix, the second phase is the monitor loop, and the last phase is the postfix. In the prefix, we know that past accesses might fail, and for some of them we do know when they fail. For all of them, we do know when they fail and when they don't. In the monitor loop, we know that all accesses do succeed, and in the postfix, we know that some of the accesses fail, and these are the ones that look in the future, and everything else succeeds. So when translating these 3 phases into actual Rust code, what happens is that rather than accessing the conditional value here, we can replace this conditional access just by the default value, because we know it would fail anyway. And in this particular case, by substituting the 0 here, we know that the whole check here just boils down to false. In the monitor loop, we then don't have to access values conditionally. We can access them unconditionally because we know the values are there. And lastly, in the postfix, the similar thing happens as in the prefix. Here, the future accesses definitely fail, so we can substitute the default value, and in this particular case, reduce the whole expression to just false. And the summary of what's happening here in this optimization is that we eradicate most conditionals, and we replace several memory accesses with constants. And both of these things can have a huge benefit, can mean a huge benefit for the performance, because they take a lot of time in the actual machine code. So we're talking about the improvement here. Let's put this into numbers. For this, we compared the compiled execution against the interpreter I mentioned before. So we used the very simple running example of the compilation first. And here the interpreter needed around 400 nanoseconds per event, whereas the compilation only needed 6 nanoseconds, which is 1.4% of the running time. And for a more involved example, we took a network specification, and here the interpreter needed 1.5 microseconds per event, whereas the compilation still needs 60 odd nanoseconds, which is around 4%. So we have a huge gain in performance here. However, even the best gain in performance is no use if it's not correct. So let's talk about the verification of the monitor. The major challenge for the verification is that in Lula we argue about streams, and streams are infinite sequences of values. So this is all good and well. However, in Rust we don't have any notion of infinite sequences of values. We only have a finite piece of memory, and this excerpt of the stream has to suffice. We know how large this piece of memory has to be, namely this is the memory requirement we computed before. And now we want to show that these values are the same as the ones in the theoretical Lula model. To do so, we introduce the ghost memory layer, and the ghost memory is only used in the Viper verification. And there are two things we have to show. The first thing is that every value in the Rust memory, this is the only real memory we have, is the same as the respective entries in the ghost memory. And the second thing we have to show is that every value we enter into the ghost memory in Viper is actually correct with respect to the Lula semantics. And to prove these two things, we have to add a couple of different annotations in the code. The most interesting parts are the invariants for the monitor loop. So let's have a look at that. So this is the monitor loop, and the first invariant we add is this, where we have a value I, and we universally quantify over this I. And I ranges between 0 and the memory consumption of A. This way we can access every single value in the finite excerpt of memory we have in Rust. And here we show that if we access the memory, the actual memory for this index I, the value is the same as the respective entry in the ghost memory. So this proves the first part of the verification. And the second part is this invariant here, where we say if we compute a new value for the toHigh stream, then this value here is computed based on the Rust memory. So this is the actual value we would get when executing the code. And this has to be the same as the same computation, but using the ghost memory instead. So this value here is purely theoretical, because we would never compute it since we have no access to the memory in the actual execution. Whereas the value on the left-hand side here is the value we get in Rust. So this way we show that, that this value here we compute in Rust is the same as the theoretical value, and this is also the value we would enter into the ghost memory. So putting these two things together, we verified that the Rust code is actually correct. Now this is all nice and well in theory. The question is does this work in practice as well? So we wanted to investigate the viability of the approach. And for this, we first started out with the simple altitude example. Wanted to see what is the performance here. Does it work? And the answer is yes, it does work. The verification needed around 200 seconds and around 700 megabytes of memory, which is it's not too much to handle for this simple example, but we wanted to see does it also scale for more involved examples. So we took the network specification and verified this. And here, since the specification is much more involved, the memory consumption and runtime also increased enormously, but it was around 1000 seconds, which is still manageable, and 3 gigs of memory. So we were quite happy with the results. As a last example, we took a flight phase detection specification from a different paper, which is arithmetically way more challenging than the other two specifications. And we tried to verify the specification, and it failed. We weren't able to do that. It always reported that something might be wrong. And upon closer inspection, we realized that there actually is something wrong with the specification. Namely, there is an implicit assumption on input streams which might not be true during the real execution. So in essence, the relevant part of the specification looks like this. We have one input, which is the time, and we have one input, which is some sensor reading. Now we first compute a difference in time, and we compute a difference in the sensor reading. And lastly, we want to normalize the difference in the sensor reading by the time. For this, we divide over the delta time. And the implicit assumption here is that time increases monotonically. This, however, is not necessarily the case. We assume it's the case, but we don't know for certain. And dynamically, if this is not the case, then the monitor would crash. This is something we definitely do not want. Thus, this is an error in the specification. We were able to find it with the verification here. This was pretty interesting to see. Then we corrected the specification and wanted to see, are we still able to verify it? And on the corrected specs, the running time was between 6 and 16 minutes, and the memory consumption was around 1.5 gigs. This was perfectly fine. However, out of the 20 runs, 2 of them timeouted. This is around 10% of this is exactly 10% of the runs, and 4 of them failed. And failing here means that either these 3 or Viper crashed, or Viper reported that some assumption could not be verified. And the curious thing is, sometimes Viper was able to verify it, and sometimes it wasn't able, despite us not changing the specification in any case. So while these tools work remarkably well, sometimes they have their little problems, and any improvement in this regard for these tools is also an improvement for our approach here. However, regarding our approach in particular, the results here are really positive because we successfully detected errors in the specification, and we were able to verify monitors even for complex specifications. So now let's see how we can further improve the monitor, the software monitor. And for this, we have to have a look at the concurrent evaluation. So assume we extend the specification a little bit by adding another sensor, a pressure sensor, and doing some computation on this. In this case, we just check whether it's below 0. Now we can compute the dependency graph once again. And as I mentioned before, the computation of trigger 2 and the evaluation of too high is independent, so we can do this in parallel. And this is perfectly possible in software. Here we use the crossbeam library of Rust, and we say we start a new scope, and in this scope we spawn different threads. In one of the threads we evaluate the too high stream, and in the other one we evaluate the trigger 2. Now this is perfectly fine. What's happening here is that we give read-only access to the memory to the evaluation functions. So here the type system of Rust already takes care of the problems with concurrency, namely the functions do not have any way of modifying the memory. So we know there are no data races. Okay, and doing so could technically improve the performance. And I'm a little hesitant here because concurrent evaluation in software is always a double-edged sword. So for the very simple specification we have here, neither the computation of trigger 2 nor of too high stream is really expensive. And having this constant overhead of spawning new threads might even outweigh the benefits. So here we have to be a little careful. For different specifications like the Altidola specification before, where we have intense computations like sliding window computations, there it usually pays off to parallelize the computations. But for simple specifications, we have to be careful. So the takeaway here is that enabling software parallelization is a double-edged sword. We have to weigh our options. Hardware parallelization, on the other hand, is a no-brainer. We can just activate it and it's pretty much for free. So that's the main idea behind deparallelization. And now let me summarize the software compilation. When you use the software compilation for the development of cyber-physical systems, you take the LODA specification, you compile it down to Rust code, and inject annotations. And these annotations help the Viper framework to verify the correctness of the code and thus the monitor. And this pretty much completes the second block. Before we go to the third block, you are free to ask any questions.